All right, this is Friday, March 12th, 2021. 1 year after our school shut down due to the COVID pandemic. This is for Physics EP, and it's going over light rays. So this is a pretty straightforward worksheet that we would do in class normally and have some fun while we're doing it. But now, in the era of pandemic, it's just you get to watch me have all the fun, and I'm not even going to do much of it. Okay, so what is a ray? Light is a form of electromagnetic radiation, and it's a transverse wave. So if I were to represent a transverse wave, not that I can draw it very well, but I should draw something that looks like a sine wave. Transverse is where the particles that make it up vibrate perpendicular to the direction of the wave travel. So wave travel goes, let's say, to the right in this diagram, and the vibrations of the medium are perpendicular to the wave travel. That's a transverse wave. Now, the beauty about light waves is that there is no particle necessary for them to travel. If this were any other type of wave, any kind of mechanical wave, then there would have to be some sort of material here. Sound, for example, which is a longitudinal wave, can't travel through the vacuum of space. It needs some material to bump into, whether it's air or a solid. Okay, so water waves need water, earthquake waves need an earth, So waves generally need a material, but light being electromagnetic, and that's a whole little talk right there, electromagnetic. These types of waves do not need any material. They are self-propagating. They are able to send themselves through the vacuum of space, which is great because otherwise we wouldn't see any light coming from outside of our planet. Okay, so what else I want to tell you about it? No doubt you remember chemistry and you love chemistry. So you'd have an atom, and there'd be the nucleus of the atom with the protons and the neutrons, and then there'd be an electron cloud around it, which we could draw as if it were an orbital, and there'd be higher energy levels. Well, when an electron, let's see, electrons prefer to be in the lowest available energy state. But you can excite them, you can give them some energy. And if you give just the right amount of energy, they can jump up to a higher energy state. With even more energy, you can remove the electron, and now you've ionized the atom. But we're not going to do that right now. What we are going to do is imagine, so I have an atom, and I've given it just the right amount of energy that the electron jumps to a higher energy orbital. Well, generally, it doesn't like being up here in an excited state. It would rather be in the ground state. So as soon as the opportunity presents itself, it's going to release energy and drop back down to a lower energy state. Now, this energy that it is released is called a photon. A photon is a wave train of energy. A photon is a wave train of energy. And for a typical atom, a photon is on the order of about 2 meters in length. Now that's not the wavelength. That's the length of this entire sine wave that we would draw that represents one photon of energy from one electron in one atom dropping down to a lower energy state. That's it. So this sine wave to scale, well, never mind to scale, but the full length of one wave train would be 2 meters from one given atom. So what we can do is get a huge collection of atoms and give them energy one way or another. And they can release that energy, and along the way, photons are emitted. If the photons are in the part of the electromagnetic spectrum where our eyes can detect them, then we see the light, literally. All right, so that's what's going on. Today is March 12th, 2021. And what we're going to do here are draw light rays. So I've talked about light. What is a light ray? If you were to look at this sine curves that I draw that represents one wave train, and then zoom way out, it would look more like that, where you'd have to zoom way, way, way in to see that that's a sine curve. Well, there's no point in drawing it like that. So when we draw a photon, we zoom out enough that we can just draw a straight line, stick an arrowhead on it, and that is a ray of light. Okay, so this zoomed way out. Looks like a straight line. You're going to draw it as a straight line. Now, when we did forces in our study of physics, the arrows that we drew represented force, and they were always to some sort of scale. So if I drew the force of gravity pointing down towards the center of the earth, and I drew a normal force, if I do the normal force longer than the force of gravity, that would mean that the normal force was greater than the force of gravity. But this scale doesn't apply for photons. So we're just going to draw the arrow. Sometimes it's convenient to have it go a long distance. Sometimes it's convenient to have it go a short distance. And whether we draw the arrow as being short or long doesn't change the meaning that it's just a photon of light. And finally, everything that we're doing on this handout is called ray tracing, which means we are propagating a bunch of photons as arrows to see where they go, and hence the directions here. It says, for all light rays, use a pencil, ruler, and arrows to show direction. Ta-da! That's why there's an arrow here at the edge of the instructions. That represents one ray of light. Okay, so on that happy note, this stuff should be pretty straightforward now. This is an old-fashioned classical pre-LED light bulb invented by Thomas Edison. It took him over 600 uh, experiments to come up with something that would actually work as a light bulb. The way they work is there's a material in here, typically a metal, let's say nichrome wire or something, and we provide it energy through electricity, and that energy is exciting electrons in the atoms that make up the material into an excited state. They don't like being up there, so they drop back down. As they drop back down, they shine light. So the question here is pretty straightforward. In what direction does light shine from a regular light bulb? Okay, so light, starting from the filament, And this light bulb travels through some gas that keeps it from burning up, really, and comes out the light bulb. But it doesn't come out in just one direction. So, what we should really do in a situation like this is draw several rays of light all coming out of the light bulb. It's not necessary that you draw lots and lots and lots of light rays, but you should at least clearly communicate that you understand this light bulb is shining in every direction that's not through the base of the bulb. That's called the bulb, the base there. So it's shining up, it's shining to the right, it's shining in front of you, it's shining behind you, it's shining to the left. It's lighting up the room. Okay, so there's the first one. Part B, the sun. Oh man, I wonder in what direction the sun shines. Okay, so as my students correctly point out, light from the sun shines in all directions. So I'm just going to draw several arrows to convey the meaning that the sun is shining towards you, away from you, in all directions. I just find it convenient to draw two lines with one straight edge, but there's nothing that says they have to be lined up with each other. And, you're just drawing several rays of light, communicating that you understand the sun shines photons in all directions. And just to toss it in there, because we will be studying astronomy as part of this course, in this case of the sun, the electrons are often completely ripped. Well, I think they are always completely ripped off the atoms. So all of the material that makes up the sun is actually ionized. And yet, on occasion, the electrons are trying to cool down, drop down to a lower energy level. And that's when they're emitting photons. But the sun is so hot that energy knocks them back off. So the sun is not considered a solid, nor is it a liquid, nor is it a gas. It's classified as being a plasma. A plasma meaning it is a superheated, condensed gas state that is ionized with the electrons ripped off the atoms because it's so darn hot. All right, now for the fun thing that we would normally do in the classroom, we have a laser. And so I want to talk about what we have is a Hemi laser. So He is for helium, Ni is for neon. This is one of the more original types of gas discharge tube lasers. The very first lasers were actually made out of solids, and they were pulse lasers, and they were invented. I think the first operational one was in the early 1960s, maybe somewhere in that time period. Maybe 67 though. Oh, okay, 1960s. Not long after that, gas discharge plasma tube lasers were invented. And so I want to explain a little bit about how they work. This, when you have the right mixture of these two gases, you have a combination that lets the electrons linger for a little while in an excited state. That's called a metastable state. So instead of immediately jumping back down to the lowest available energy level after you give them a boost up, they linger for a little time up here. Long time scale for an atom may be short for you and me, but they linger in this metastable state. Now, this gas discharge tube is filled with lots of atoms, not just one. And sooner or later, at least one of these atoms is going to now finally drop down to a lower energy state. From the metastable excited state to the preferred lower energy state is always the same amount of energy. And so the wavelength, which is an indirect way of measuring the energy of a photon, the wavelength is 6328, maybe, angstroms. So 632.8 nanometers. You know, I think I'm going to bother looking this up because I am recording it. So I'm going to pause for a moment. So having checked with Lord Google, good old Wikipedia says the helium neon laser emits at a wavelength of 632.816 nanometers in air. And so, dang, uh, got it. The vacuum wavelength 632.991 nanometers. So 633 nanometers. Ta-da! I remember this from high school when my science teacher lent me a laser. Okay, so back to the story. In a laser, which is light amplification through stimulated of electromagnetic radiation, in case you didn't know that, this particular photon will start heading off in some direction. And because it's at the same energy state uh, as a neighboring photon, the neighboring photon will start to join with it and emit its photon. But the beauty of it, it will have exactly the same phase, this wavelength. And so we call that being coherent. Coherent is in phase. That means the crest of one photon matches the crest of another photon from a nearby atom. Remember, the wave train can be 2 meters long. So somewhere in that 2 meter distance, much shorter, tubes are actually just like 6 inches long. A photon is emitted, and another one, and another one. It's sort of like, what do you call it? A cascade effect, a chain reaction. So one triggers a whole bunch of them to emit their photons, and they're all coherent with each other. So on a typical Hemi laser gas discharge tube, you have a tube, maybe it's 8 inches long or something. One end of it will be a mirror, so that when the light gets to it, it just reflects back and does another pass. The other end has a mirror as well, but this end has a little tiny hole in the mirror. And so now the coherent laser light, all at one pure wavelength, is emitted from this hole while the rest of it just keeps sloshing back and forth. All right, so this brings us to part C. What should I draw to represent laser light? All right, I see I forgot to record my exciting lecture. I hate to think how much I didn't record. I tried to explain how helium neon lasers work, how they're coherent with the light coming out one end, and I paused it and asked the student what to sketch and then forgot to resume. So the student said, draw a single ray coming out of the laser pointing the direction that the housing is pointing. And that is correct. And then I started chatting about how the laser beam expands a little bit due to the laws of physics. So even though it starts as a little tiny dot that's smaller than a quarter of an inch diameter out of the laser that we have at school, after it's traveled, let's say 2 miles, that spot would be maybe a foot or a foot and a half in diameter. So it does expand slightly due to the laws of physics, but not enough that we would care about in our ray tracing here. So just draw one pure straight line that represents a laser beam. And then I mentioned, gosh, we have retroreflectors on the moon, and using distance equals speed of light times time, We actually measure the distance from the Earth to the moon with lasers and telescopes, and we can measure that distance to the nearest inch or so. Great. Next one is a candle. So, in what direction does light shine from a candle? Okay, the student correctly points out that in the situation of a candle, we would draw rays of light pointing in all directions except through the candle wax. Can't shine through it very well. And by the way, I want to mention what a candela is. Candela is the brightness of one candle at 1 foot distance away from you. So before electricity was found or worked out as a way of making things shine, this was the standard unit of brightness, one candela. All right, next on the handout number 2. State whether each object below is rough or smooth. And when we say rough or smooth, we don't mean on the scale of how it feels to your touch. Excuse me. We mean on the scale of photons of light. If light hits a very smooth surface, then it can reflect in primarily one direction off that surface. That's called the law of reflection. When it strikes a rough surface on the scale of the wavelength of light that we're talking about, then it tends to scatter in all directions. So, how should I classify tissue paper, rough or smooth on the scale of photons of light? Okay, students correctly would classify tissue paper as being rough in that when light strikes it, it tends to scatter in all directions. What about glass? All right, student says smooth, and that is correct. We consider glass to be a smooth surface. Now, I'll just leave it at that for the moment. How about a wall? Yeah, a wall would be considered a rough surface. Hmm, how about a mirror? Yep, smooth. So, in fact, a detail about a mirror, if I had a window, let's say here's a window made of glass, it's smooth. The light, most of it transmits through the window. And for visible light and typical glass that we use for windows here, about 4% of the energy of the photons reflects off the window. So you can see your reflection off a plain sheet of glass. Anti-reflection coatings are special additions to the surface that cause light to interfere with each other, with itself, in such a way that the light energy is knocked way down on the, let's say, the reflection. Anti-reflection coating. A mirror is a situation where, let's say, by the way, we're going to use this symbol to represent a human eyeball. Okay, so this kind of is the generic symbol we use for eyeball. There's the person's iris, and the light waves go into the person. If this were a window, we can put a coating on the back of the mirror, like silver, and as if nothing else. And so the light coming from this side would go through the glass, reflect off the coating on the back, go through the glass again, and into your eye, and that's a mirror. This is a back surface coated mirror. In astronomy, we don't like the distortions caused by going through the glass twice. So in astronomy, we put the coating on the front of the mirror and call this a front surface mirror. So it's much more delicate, more easily damaged because here the glass is protecting the coating. Here the coating is not being protected by the glass, and therefore it can oxidize over time. It can react with oxygen, and particularly if it's something like silver, uh, become discolored, lose its reflectivity. In the case of our telescopes at school, we've had at least two telescopes now with their primary mirrors recoated. So we sent them off to a place in Santa Ana, and at that place they remove the coating and clean up the mirror and put a fresh coating on, and now it's good for another 10 to maybe 20 years at most. All right, so that's a mirror. What about skin? How would you classify skin? So even though I use the phrase like smooth as a baby's bottom, skin on the scale of wavelengths of light would be classified as rough. And finally, so yeah, the student is correct. Finally, an overhead screen, which means when you go into one of those old style, ancient pre pandemic movie theaters, ha ha ha, well, you're coming back, maybe. The movie screen that you're looking at is optimized so that you can enjoy seeing the movie that's projected on it. So that leads to the interesting question: how would you classify the overhead screen that you see in the front of a standard classroom or in a movie theater? Rough or smooth? Okay, so even though the student is speculating that overhead screen is smooth, I would say careful. If it were smooth, that means the screen would be like a mirror when you look in it. And these screens, when they're not having images projected on them, are they look like white things, sometimes silver looking. So really, they are rough surfaces, so that no matter where you're sitting in the movie theater, you're seeing light reflected from the projector off of the screen. If the screen were smooth, like a mirror, you wouldn't be able to enjoy seeing the movie. You would just have light shining into your eye from the projector. And even at that, you'd have to be sitting in just the right seat to even have that happen. So, screens are rough. Now, they have different quality screens, but in general, the goal with a projection screen is to have the light that shines on it reflect in many directions, as close to 180 degrees as they can to all directions, and preferably with as much intensity across all those different directions. So whether you're sitting way off on one side of the movie theater or in the middle or way off on the other side or up in the balcony, you get to enjoy seeing the movie. Okay, which brings us to number 3 here. Draw enough light rays to show how laser light reflects off the wall. I'm going to pick up the pace because it's a little late in the period. So we know from before that a laser beam emits a coherent beam in just one direction. And we're going to use this vertical line as our wall. It's a rough surface. We said walls are rough. And for rough surfaces, the light scatters in all directions. So what you should draw are enough rays of light to convince someone looking at your paper that you understand that light scatters in all directions off the wall. And I mentioned we used to do this activity in our classroom uh, because we have a red Hemi laser. And what we used to do for fun is have a student um, clap together some erasers in the old days. So chalk dust would go up into the air, and that would let you see light reflecting off the chalk dust as it passes through the room. And so, like in the Hollywood movies, where they take the trouble of making the air dirty, you would be able to see the laser beam going through the room. And then for fun, we happen to have some mirrors. So I used to have several students around the room each hold up a mirror, and we would try to bounce the light from mirror to mirror to mirror to mirror to mirror around the classroom. Ta-da! That was fun. Now, wherever the laser beam hits the wall, all students in the classroom can see it because whether you're uh, close to the wall or across the classroom or standing up over here or sitting down over there are rays of light scattering from the wall into your eye. Whether your eye is over here or your eye is over there, light enters your eye. And number 4, draw enough light rays to show how sunlight reflects off his head. Well, you should draw rays of light coming from the sun to his head. So draw a ray of light coming from the sun, hitting his head, and there's more than one ray of light coming from the sun. There are countless trillions of photons of light from the sun hitting the top of your head per second on a sunny day on Earth. So at least draw a couple rays. And then for each one, I'm not going to bother with the straight edge. Just clearly indicate you understand that the rays of light are going to scatter in all directions. And this is what lets you see the person in sunlight. Which brings us to number 5. What are the 3 necessities for an object to be seen? Okay, sadly, 3 guys that I called on couldn't remember any of the necessities for an object to be seen. I'm sure if I called on the ladies, they would just recite it. So first of all, we need a source. Something that is emitting photons of light. And photons are created by adding energy to atoms and moving their electrons up from the ground state. In the case of a light bulb, we're doing that with electricity. In the case of the sun, we're actually doing that through nuclear fusion. In the case of a laser, we're doing that again with electricity. In the case of a candle, we're doing it by a rapid exothermic chemical reaction. The candle wax is burning in oxygen to create carbon dioxide, water, and release heat and light energy at the same time. A source, a source, a source. Definitely, we need some sort of source. Finally, we need some sort of a detector, something that does what a human eye does. So, detector would be the third thing. Example would be your eyes, the camera focal plane array, a photoresistor, which is kind of like a single pixel of a camera, but not quite. It's an electronic device where it responds to photon energy hitting it and makes an adjustment electrically. Okay, so there's one last thing. Number 2, what do we need between a source and a detector to actually see an object? Like here, what would it take to actually see this person? We have the sun. I could have a person standing off over here with their eye looking towards this person. If there were a tree between the two of them, then you would not be able to see the person. So the second condition that we need is an unobstructed path for the light to take. If you block it with a tree, a wall, a building, closing your eyelids, then your detector isn't going to see anything. That finishes the front side. Let's get now to the back side of this fun-filled, exciting educational handout. Alien visits Earth. Alien is new to Earth. He has fully functional eyes. The candle is the only source of light in the room. Candle, pencil, alien. Part A. In what directions do light rays leave the candle? Okay, so a student replied, the light rays go up just past the wax. So I'm going to interpret that to mean, of course, the student means the light rays from the candle are going in every direction other than through the wax at the base of the candle. And strictly speaking, they're shining on the top of the wax and then they're blocked from there. So they actually go, whoop, don't bother joining that. Okay, so light rays from the candle being emitted in all directions except where it's blocked. Part B, it's a yes or no question. Can alien see the candle? Nice. So the answer is yes. And it says part C, draw the ray of light from the candle that causes alien to see the candle. So I haven't drawn it yet, but clearly source, detector, unobstructed path is what it's going to take. So draw a ray of light that hits at least one of alien's eyes. Ta-da! There's part C. Part E. Part D. Can alien see the pencil? A yes or no question. All right, so the student says, yes, alien can see the pencil. Part E, draw the ray of light from the candle that causes alien to see the pencil eraser. All right, so the student says, draw a ray of light from the candle to the pencil. And in particular, it's not just the pencil, we're targeting the pencil eraser. So as you look at this diagram, we interpret this as being the pencil lead, and that is pencil eraser. So I'm going to draw a ray of light that starts with the candle flame and hits the eraser. All right, and but with guidance from the student, the rays of light hitting the pencil eraser, well, the eraser is a rough surface. So rays of light are going to scatter from the pencil in all directions, including back to the candle, by the way, right? But the ones that we care about that let alien actually see the pencil eraser happen to be the rays of light that scatter into the eye of alien, or yeah, into the eyes of alien. Okay, so there is letter E. Letter F, draw the ray of light from the candle that causes alien to see the pencil lead. I think that should be kind of obvious what we're going to do. Well, that was torturous, but I got a student to tell me, all right, draw a ray of light that starts with the candle shining so bright and hits the pencil lead. Now, of course, it scatters in all directions that aren't blocked by the pencil, but the ray of light that we care about is the one that reflects off the pencil lead into alien's eyes. All right, so there's number 6. Number 7, the very last one. One day, alien notices that the sun and the moon are in the sky at the same time, something that happened here on Earth just a few days ago or last week. And then part A and part B, draw the ray of light that causes alien to see the sun, and part B, draw the ray of light that causes alien to see the moon. I'm now going to stop recording.